Hello everyone, my name is Jack Garrity.
I'm Victor Sefritz.
And we're with the American Nuclear Society at UIUC here. And today we're with Professor Daniel Andruczyk. Professor Andruczyk is an associate research professor who is at the Center for Plasma Material Interactions here on campus. He runs the HIDRA fusion reactor, and his research focuses on plasma material interactions in fusion reactors and molten lithium as a first-wall plasma-facing material. He holds a doctoral degree in plasma physics from the University of Sidney and has had previous appointments at the Princeton Plasma Physics Laboratory and the Max Planck Institute. Welcome.
Thank you. Thanks for having me. I'm excited to be doing this, and that I'm the first one that you're interviewing.
First one.
Yeah.
That's right.
Yeah, very good. I love it.
So, Professor Andruczyk,
Yeah.
our first question was, what do you teach at the University of Illinois as classes, for
Oh.
example?
Yeah,
and what do you research, and can you tell us about the basics of your research?
Yeah. Okay. So let's go. What I teach. There's actually a whole number of courses that I teach, ranging from the freshman level right through to the graduate. So I teach a couple courses on energy sources and energy systems at the freshman and sophomore levels, MPRE 101 and 201 I've taught, which I've taught. I also teach an intro plasma course, which focuses on sort of giving the basics of plasmas to students, but also then looking at it's the first introduction of the application, so seeing, plasmas really are sort of everywhere. And then at the graduate level, I teach NPRE 526, which is a plasma material interaction course, 527, which is the gaseous electronics and plasma technology course, and I also do a special topics course on basically fusion engineering, and basically looking at how to build a fusion reactor. It's not even the plasma physics, it's just what's the engineering, some of the engineering that we have to worry about in building a fusion reactor. So that's what I teach. And in terms of the research that I do, my interests are in understanding the materials, particularly the materials on the inside of the machine, how they interact with the plasma, because basically if we can't find materials that we can build a machine out of, then everything else is moot. All the plasma physics, everything, doesn't count if you're going to be melting a machine and you have to replace it every 2 days or something, right, if you don't have the material. So it's all about understanding the interaction and how can we either find a new material or find solutions to the current materials that will help tolerate the damage that we get. That's sort of, in a nutshell, what I do. I should also mention, with all that I'm also the director of the department's Master of Engineering and Plasma Engineering program, which is it's a professional master's program that allows for students to get masters. We're sort of mainly focused at the semiconductor industry level, but we're trying to expand that out to other plasma industries. But that was sort of the original focus of it, and sort of where we're going with all that. So, yeah.
Very cool. That's awesome.
Yeah.
There's you got a very busy man, it sounds like.
Yeah.
So, of all those classes you teach, what do you think is your favorite? I know you do a lot of like interactive demos and stuff. What are your favorite things to teach? And
yeah, they're all fun to teach. I mean, they really are, because it's bringing in not only knowledge that I've gained and that I can impart, but it's like the freshman courses. I inherited those from other professors who've since retired, right? And so, you build, you take what they've done, you put your own spin, build on that. You bring in your own experiences on the various, topics and that. And so it's sort of fun when you get to share, what you've been able to do with people. And with that, I do that with all my courses. I try and bring in examples of of my own experiences in life, in research, wherever. Maybe colleagues have had experiences that I'm aware of, and I can bring those in. So I think it's very important that it's one thing, when we teach this, we often will, we have a textbook, let's say, that we use as our reference, and you sort of go, section by section, talking about that. That can get boring. So if you can add something where you talk about your experiences, you're bringing demos, which I like. If I can bring a small little thing just to show people, with one of my classes, we will go and out to the lab and I will show plasmas. I'll do sort of these, plasma displays. So because a lot of students have never really seen a plasma, haven't realised that they have seen plasma, until you show them. You go, hey, this is a plasma, and they go, awesome. So, I enjoy all those. 321 was a course I developed, so I really enjoy that. The special topics is a course that I developed as well. So, they have a lot of my personality in them, kind of thing. The other courses I inherited, but they're fun courses. In learning those, when I took them over, I enjoyed those because you learn things. You learn things from a different perspective as well, that others have, and that's always the name of the game in what we do. It's always you're learning. You're trying to get a different perspective on things.
Well, thank you very much, Professor Andruczyk. And personally, I really like demos and courses in which there are demos, so we can, as students, get a real hands-on learning and actually see what you are teaching. So I think that's really important. And we had another question, which is actually 3 questions, but into one big question.
Oh, okay.
Can you tell us about your path into this field? What got you interested in fusion, and how did you wind up at the University of Illinois?
Right. So, how long did we have? 1 hour? All right. Let's see if I can do the short version. All right. For all those that know Spaceballs, the reference from Spaceballs, a short version. Right. Okay. So, how do I get into fusion? Well, that's a little bit of a not convoluted, but it's an interesting path. I was always interested in all things nuclear. So my interest actually from day one has been nuclear. So it's sort of feeling that I'm in a nuclear department. But specifically what sort of got me interested in physics and all that, I'm trying to think now, I must have been maybe 13 years old. There was a National Geographic. My father collected National Geographic from the mid-70s all the way through to, I think, 2000. I'm just trying to remember. I think it's April 1985 is the edition. Anyway, in there was a whole thing on particle accelerators. I think they just discovered one of another quark or something, and so they had this big spread on all the fundamental particles and CERN and Fermilab and everything. I think they talked about the work at that time. I think Representative Foster, who's a physicist in Congress, he was one of the principal scientists working on that, and that sort of just inspired. I was like, yeah, that's the kind of thing I can see myself wanting to do. And so I really just started to dive into that, understanding physics, science, and so the nuclear world a lot more. And then, so this was I was still living in Sydney. Then when my parents retired and we moved up to Brisbane, the university up there didn't really have a nuclear program. So I still went into physics. I did that. I did my my honours degree in laser physics. I was actually basically a rocket scientist for a year. I was working, doing stuff on hypersonic shock flows and things like that. And it wasn't then, I did an internship at the Australian National University in Canberra in 1998. It was at the end of my third year. And I was working, they have a particle accelerator, so they had a nuclear program down there. They had a small Van de Graaff particle accelerator, and I went down there. We were doing, looking at cosmogenic beryllium or boron, I don't remember, I think it was boron, cosmogenic boron production and stuff. And at that time, there was an article came out in Scientific American. It's amazing I can still remember this. There was an article in Scientific American that came out that talked about fusion, and in particular, I think NSTX had just been built, and they were talking about using liquid metal as the wall. So, and I was just like, oh, that sounds really cool, fusion. And I got talking with the professor I was working with, and I said, oh, it's a shame. This is what a young person at the time says. They, without doing any research, they go, oh, it's a shame Australia doesn't have a fusion reactor and this and that. He goes, what are you talking about? There's one right across the road in that building. I'm going, what? He goes, yeah. Tomorrow lunchtime I'll take you over and I'll introduce you to the head of the department, who was an American, Jeff Harris, who very well known accelerator guy. It was a accelerator that they had down there. And sure enough, we went over the next day, introduced me, and I saw the machine, and I was just like, oh no, that's what I wanted to do. That's what I wanted to do. So all the particle accelerator stuff was cool, but going and what I saw was, I always wanted to do like what people call big science, the big machines. But this was going to be science that is going to be directly applicable to the betterment of humanity by producing energy. Back then, the whole clean energy debate was not really a thing yet. Climate change was, people were sort of talking about, it wasn't a big thing. We're talking about 98, 99. And so then I went back and did an internship the following year with them. And I didn't work on the fusion reactor. I worked on plasma antennas, basically on something we dubbed it stealth radar, because you can make a plasma column in a fluorescent tube. It will basically, and because it's a conductor, and if you tap into it, you can transmit and receive on it. But you can imagine you can detune it, so enemy radar, let's say, you detune it to their frequencies and it becomes transparent. And so it becomes basically like a stealth antenna. But the other cool thing about that, and I always like to say, the way we built it was you could hold it in your hand, and it was a lightsaber. And so for 3 months, I worked on basically lightsabers, I say.
That's awesome.
So, yeah. So that then from there, I was in plasmas, and then I applied to various programs, and being a Sydney boy, University of Sydney, I had won the a great plasma program, and I decided to go there. And it was very collaborative with ANU, so I built a diagnostic for fusion reactors, which got me to work on the reactor. I made a lot of friends to this day. We keep in touch, and so that's sort of how I got into fusion. From there, when I got my PhD in Sydney, I got my postdoc in the Max Planck Institute in Greifswald. So this is the German national lab where they built W7X. So W7X has been in the news a lot lately because their performance, they've been really ramping up the performance on that machine. But I remember that thing being built and watching all the coils and everything, 3 a.m. These are massive coils being delivered at night. Everyone, the whole town, it's a small town of maybe 50 or 60,000 there. We're all lining the streets, having a beer, watching this parade of just stuff that was being brought in, because they were manufactured I think in Italy they were manufactured, so they brought them up. So yeah, it was a whole thing. It was great. I was working on Vega, which is now HIDRA, but I was working on that machine, and right next door they're building, like a €1 billion, fusion, accelerator next door, and again, lots of great friends, lots of really amazing memories from that place. It really gave me a lot of the opportunities that have come up over the years, and so once sort of I finished that in 2009, 2010 I came here, did another postdoc for about a year, but then I got promoted up to a research engineer, got stationed over at PPPL. I was there for 2.5 years, and in that time, the two big things was we got word that Vega was up for grabs, so we grabbed it, renamed it HIDRA, so we have HIDRA, and also met my wife literally the same day as we sort of. I got the okay to I said, yeah, we'll take HIDRA. It was also the same day I met my wife. So.
Sounds like a really good day.
It was very productive. I was very productive with my time, yeah. I was very productive, efficient, as you always have to be, yeah. Do I answer everything? Is there another
that's great.
third question?
Yeah.
That's awesome. So, a follow-up, you've obviously worked on like a ton of projects. What projects have you worked on that have been your favorites, like so far, or things you were like really excited about and you're really happy that you got a chance to work on?
I mean, everything really, because every project is a stepping stone to where you get to. All the way back, to my my PhD, working on H1, doing diagnostics, I learned all about diagnostics. So, in fact, so from when I submitted my thesis so it was about a year-ish between me submitting my thesis and when I went to start my postdoc. So University of Sidney actually employed me for almost a year-ish, somewhere around there, to do some diagnostics on another device I had, a cathodic arc. It wasn't a fusion reactor, but there was a new little device they built. They need to get some diagnostics on there, so they employed me to do a whole bunch of laminar probe measurements and that. But the funny thing was they didn't have money to hire a person, but they had money for equipment. So the workaround was they wrote me in as a laminar probe. So I was like a $50,000 wire for about a year technically. So I could do the diagnostics. I used the helium beam that I developed my PhD. We used it on that to do some measurements for verification. And there was so it was a lot of fun. So doing all that, working on that. Then and then working on Vega, and then seeing W7X was amazing. And so in between all that, it wasn't so much I did work, but getting to visit a lot of other devices and seeing other devices. So during my PhD, I did a lot of, we collaborated a lot with the University of Hiroshima. So I spent a lot of time in Japan, in Hiroshima, doing work there. And I got to see LHD. And over there, I've also saw OSDEX. I got to JET a couple times, and saw that machine. So, you get a lot of experiences with all that. Doing stuff on NSTX was amazing. And of course, the most fun is that we have HIDRA, doing everything on our own machine. I should also, I can't not mention all the work we did on East, and that work really opened up a lot of amazing results and a lot of opportunities that has led us to being sort of the lab that we are in terms of knowing and understanding the way lithium interacts with plasmas. So, yeah.
Very cool. Lots of reactors. It's like you've seen pretty much everyone.
It's like that. You need to. The more you see, the better. And you can experience it. It's important, to get these experiences, whether it's through an internship or maybe at a conference, going and seeing. A lot of the time conferences will do tours and things like that. These are really important, because this is where you start to develop sort of the knowledge base outside of what you're learning here, or wherever you're based. And so you, as a student, as a researcher, your primary goal should be to learn, right? You're always learning something new. And so whether it's, even if it's outside of your direct thing, if you want to go and tinker around and learn this little thing, well, go ahead and learn it. I mean, that's what you're here for. That's what we're all doing. So, yeah.
And maybe in terms of this knowledge, for people and for students who are passionate about nuclear engineering, fusion, fission, what are the best skills that you recommend for these students to succeed in their career, in their research?
So, that's a tough one. Communication is a big one. And when I say communication, it goes both ways. It's being able to communicate, but also to listen. Because if you can listen and take in, that's where you learn, or where you can form, your own ideas and things like that. So that's a big one. And I always encourage my students to not to shy away from asking the dumb question. Because I always say there's no such thing as a dumb question. Particularly there may be, 10 other people that are thinking the same thing and maybe too timid. I'll give you an example. I was in a meeting not long ago, and we had some potential new collaborators that might be coming in, and all the old guard, all the guys had been there for a long time. We're throwing around all these acronyms everyone knows, and one of the, a very well-known scientist, but not really part of this field, he just goes, what is this and what is that? Can you just tell me what is that acronym? I don't know this acronym. I need to learn. And this is a very well-known scientist. I'm not going to give away any names here, but it's the thing is, I could probably see there's maybe another 3 or 4 people that were on that call that were probably in the same boat, right? So ask a question. There's no such thing as a dumb question, I say, because there's always someone else might not have the knowledge. Be sociable, because that's where you make your contacts. Sociable and personable. I'm always a big advocate that when you go to, let's say, a conference and that, be very much, willing to go and talk, sit down and talk, over a coffee, because that's actually where you learn. It's one thing to sit in the talks. The talks are all well and good, but it's people very niche, specific things. But when you really want to have a really good discussion, it's all the stuff behind the scenes. That's where all the magic happens. That's the true value of the conferences, It's all the stuff behind the scenes. That's where you learn stuff, where you find that someone else has an interest in what you're doing. Oh, let's set up a collaboration. You might find out that there's going to be some funding coming down the line, right? And so you can start to come up with an idea for what you want to put in for that funding, right? So the sociable aspect is also really important. In terms of work, particularly with what we do, flexibility is important. You need to be able to have an ability to be agile with your work sometimes. You might think you're doing this, and then something happens, and you need to be going, whoop, no, we're going over here now, right? And be okay with that, because sometimes you got to follow where the story's leading you, rather than you writing the story's trying to take you over to where it needs to be, and that's sort of in terms of the main line of research, so how that happened with me. So yeah.
A lot of skills that we actually need to learn for the.
Yeah, I mean, of course, you got to know your physics and all the academics. That all has to be there, but yeah, you have to be willing to listen and be able to take in what others are saying. Sometimes you may not agree with them, and that's fine. That's where debates are, but you still have to be able to let them have their say, right? Because you never know, they might make a point that you go, okay, I'm sort of on board with that. And you have to be willing to change your mind as well.
Okay.
Yes.
Very valuable. Very valuable. Well, kind of switch gears here. You mentioned HIDRA a few times. I feel like it'd be a shame not to talk more about it.
Okay. Yeah.
So, if you could tell us a little bit about, what is HIDRA? What experiments do you do with it? How is it similar or different from other fusion reactors you've seen?
Yeah. So HIDRA is, the acronym stands for the Hybrid Illinois Device for Research and Applications. It's one of the oldest running machines in the world, but one of the youngest in America. So I mentioned we got this from Germany. The path of HIDRA to here actually is a very long one. It started in 1975. It started life as a tokamak, the Vega tokamak in Grenoble in France. So it's actually a French machine originally. And so after several years, it got then converted to a stellarator, but they kept all the tokamak guts of it. So the central solenoid and all that was still there. So you had the stellarator and tokamak components. So that's why we call it the hybrid, because you can run both modes if you want. I think it's the only device that really has that true capability. I think Auburn, their machine has something hybridization as well. But yeah, we can very much. I mean, we pretty much run exclusively as a stellarator. It's the more useful mode. But if we ever really need to put a tokamak pulse in, we could. So anyway, so once so that happened, we're talking like 1980 or so. Then it was around for a couple more years. It then shifted over to the University of Stuttgart. They had it for until 2000, when the German government was in order with German reunification. So there's a lot of history got around it. So yeah, back when the collapse of the Iron Curtain, you had East and West Germany come together, and there was a real push by the German government to help economically the former East German states. And one of these initiatives was we're going to build some new national labs and have this big scientific push. And so one of them was a new fusion lab, which was in Greifswald, which was going to be exclusively stellarators. All the tokamaks were going to stay in Munich, in Garching. And so they went ahead and built the stellarator lab, designed W7X, and so they were building that. While that was happening, they're like, well, we should at least have a machine where we can do all the diagnostic testing, the heating testing, test the control systems and everything, all of that stuff. So they go, all right, we're going to grab Vega and we're going to move it to Greifswald. And so that's what they did. 2006 was when I went in with my postdoc. But it was around June 2013, I was at the SOFI conference in San Francisco. We'd just done a tour of the National Ignition Facility, and the director of the lab in Greifswald, Thomas Klinger, and a whole bunch of the other W7X guys who were good friends of mine. We were chatting, this and that. We went to the conference dinner. We were all having, had dinner. We had a couple of drinks, and we're just chatting. And I was just like, so what's going to happen, with Vega? I think one of the other researchers, Andreas Dinklager, he was the one that sort of put it in my ear, that this could be an option. So I asked Thomas, and I said, oh yeah, we'll give it to someone, or we'll scrap it. I'm like, oh, all right. So made some phone calls and called the director of the lab, Dave Ruzick. He called the dean and the head of department, who was Professor Stubbins at the time, and back then was Andreas Kangelaris was the dean of engineering, and I would basically say, yeah, we want our own reactor, sure. We'll make it work somehow, right? So I went back and I said, all right, Illinois will take it. And yeah. And then I think it was a few weeks later that sort of the negotiations. So at that point, sort of people higher up than me did all the negotiating and all that. But a year later, I went over there for about 8 weeks to pull it all apart. Got a company to put it all back together and shipped it here. They shipped everything in about a week and a half. And true in German efficiency, they said, oh, it's going to be 4 weeks. And a week later, I get a phone call, it's in Chicago, we're bringing it tomorrow. I go, no, you're not. No, I believe we've got anything ordered. I was at another conference, I was in New Orleans at APS when I got the phone call. So I ended up not doing anything at the conference because I was on the phone with FNS and trying to organise a crane and everything, storage, and I was just like, it was just like, so that was fun. And and about a week after that, we finally had it come down. And it took about a year and a half for us to put it all back together, and had our first plasma in April 24th or 25th of 2016. So we had a big shindig. It was MPRE open house, and so we timed it for that, and I think on YouTube I've got the video of the speeches and the first plasma on there. So it's about a 15-minute video. You can watch that.
I've seen it before I even applied here. It was one of the things I did. And I was like, this is awesome.
It gives good opportunities. And so we basically rebuilt it the way it was in Germany. I mean, why fix something that's not broken? I remember when we first switched it on, Vega, but it had this certain hum to it when it worked, right? You always knew, so it had this like high pitch wee kind of sound to it. So when we first switched it on, I heard that sound. I'm going, yep, we've got it. It works. You know, I know it's not the best way going by sound, but sometimes there are these little things like that tell you, you've done it. You know, everything's good when it works. So yeah, and so we've been operating since. You know, no problems yet.
That's awesome.
What was the rest of
Do you want to elaborate a little bit more on the research that you do with HIDRA?
Yeah. Well, the reason we got HIDRA is, we do plasma material interactions. In particular, we do work with liquid lithium. A lot of the machines around the world, the PMI, it's not high. It's not that it's not high on the priority, but there's so many people that are trying to do their own thing. Getting time to do anything is very difficult. The diagnostics may not necessarily be there unless you somehow got millions of dollars to convince them to install and all that. So having your own machine where you can do all this yourself is very valuable. And so that's what we do, and we've built a materials analysis test stand which allows us to put materials in that and directly have them be impacted by the plasma, and we can move them at different distances and look at different effects. And it also allows us, we can put lithium on there, and so it's one of the ways we can get lithium into the machine. And the big thing is about HIDRA is that it's a true steady state machine. What I mean by that, most machines around the world are pulsed. And some of them are pulsed because of their design, like tokamaks are inherently pulsed machines. A lot of the stellarators are pulsed purely because from infrastructure, it costs millions of dollars to get the industrial rectifiers and everything to get a steady state machine. And universities a lot of the time don't have those resources, so they get capacitor banks and they try and sort of do the experiments pulsed. We were lucky that the Germans took the time and money to actually do all that, and they got the industrial rectifiers which allowed them to go and operate at steady state. And we inherited all that. We got all that, which allows us to operate at steady state as well. And when I say steady state, the pulse machines might be 100 milliseconds. You might, on the bigger machines, they might push it out to maybe 5 seconds. We don't bother with anything under 600 seconds, right? And people argue, well, steady state in the plasma world is really anything sort of above, sort of a certain confinement time, which is maybe milliseconds or something. Okay, sure, you can call that steady state. But what we're talking about in fusion, when we talk about, I'm talking steady state is, well, we want to have something that's operating all the time. Well, and this is sort of that step to be able to do that. And we pushed, we did one sort of experiment a couple of years ago with tokamak energy. They were interested in doing some plasma chemistry with the walls. It was a very interesting experiment. They said, just run the plasma and do nothing else. I'm like, okay. And they said, but run it for 3 hours. I'm like, I'm going, okay, this will take us right up to our temperature limit. I think we can do this. We didn't go to a super high field. We were at what we call low field, which is about 0.1 Tesla. But we ran a 10,000 second plasma. We just let it go. I mean, we had pizza. It it was an exciting but boring experiment because we literally were doing nothing. We took turns, in the control room who would make sure that nothing was going bad, but we'd go, we'd have some pizza, come back, do something else, play some games while we're... But the thing was, we were looking at what the background pressure was doing. And we saw some very interesting stuff. And that alone sort of... It got us a little bit concerned for future operations, for reactors when they go steady state, because there will be all this chemistry. We were seeing fluctuations in all different stuff coming off the walls and everything in different places. So, we were monitoring different parts of the machine, and it's not all uniform. So depending on what you have in some section, it's going to give stuff off differently. So there's just so much happening there. And we were just like, ooh, this is something has to be dealt with, So it's stuff like that, that we can do with it. But the most exciting thing is the lithium work, and in particular the helium work that we've done with lithium, which has been, I think, has really sort of set us apart from a lot of the other programs in understanding that. I don't know if you want me to talk more with another question with that, or do you want me to continue with what we did there?
No, keep going.
Yeah, keep going.
So, fusion has a couple problems, and one of them is it's the helium problem. Helium is a real pain to get rid of. It doesn't pump very easily. It's a tiny, tiny atom. So, turbo pumps don't pump it very quickly. It takes a long time to pump. Cryogenic pumps don't work. And, there are some ways, using frosted argon to try and trap the helium, but ultimately you have to shut down the cryo pump, warm it up to diffuse everything and pump that out, right? So it's not a convenient way of pumping it. Thing is, if you can't pump helium, helium's a byproduct, right, of your fusion reaction. Deuterium plus tritium, the byproduct is helium plus a neutron. The neutron we take in the blanket to breed tritium and to do our, get our heat to boil the water or however that cycle is going to be to produce electricity. The helium, that's go back into the plasma, and you want it there initially, because it's carrying 20% of the energy from the fusion reaction, and so it's what's going to keep heating the plasma. It's what gets you to ignition, to what allows you to basically switch the heating off, and the plasma self-ignites. It just sits there and just stays hot like the sun, right? So, but eventually that helium has to come out. If you can't get it out fast enough, it will build up and build up and build up. And very quickly, and when I say very quickly, within a minute, it can build up and be the main contaminant and can kill your plasma, right? Or radiates all your power away. I mean, you'll get helium plasma, but your fusion stops, right? So you need to get rid of that helium. And so everything that people do in the diverter, it's all about how do you get rid of that helium out as efficiently as you can. So that's one, and so we looked at, the other problem with having all this helium in the machine is when the helium does eventually get to your diverter to the surface and interacts with this, it has to interact with the surface in the diverter to neutralize and then to try and get it out. It comes in with a lot of energy, and your surface is already operating at a high temperature, several, 600-700 Kelvin. And what you find is that you start getting these interesting features, these tendrils that start to form in a helium environment called tungsten flux. So tungsten's the main solid material that's used for this. And this is a problem because it is very brittle, it can easily sort of get flaked off and become dust, and then you've got high Z contamination and radiative losses, and becomes a real problem. So we were looking at initially how can we use lithium on tungsten to protect it from helium. So we're like, all right, let's run helium plasmas. We're going to get some tungsten. We're going to put lithium on it. We're going to shove it into the plasma, and we're going to let it do its thing. And we'll do comparisons, etc., etc. So we go, we did our baseline test with tungsten and all that. We even think we saw some fuzz, all the the beginnings of fuzz formation in tungsten, and we put lithium on, and then all hell broke loose inside that machine. I remember, so my former student Andrew showing, we were there, but we ran it. This was in the afternoon. This is like COVID time, maybe just before COVID, 2019, when we did the first, what we call the Zeus shot. So there's a Greek theme that runs through all this, and we put this thing in there, and we just start seeing the plasma behaving weird, and then we start seeing sparks flying everywhere inside. And I remember we both looked at each other and we're like, do we shut down or do we keep going? And I was just like, hey, we got this machine to do exactly this, where we can fail things, have these sparks. Everyone else might be terrified of that, but no, this is what we're here for. So I said, let it run. So we ran our 600-second shot, pulled this thing out. This thing got destroyed. And it was really funny. We had a tungsten sample, but we had these molybdenum clips on it, and the molybdenum clips got welded onto the tungsten. So it means we were pushing 3,000 degrees or something on that surface. I mean, the rest of it, which was tungsten, all got like melted out, and like it was pretty amazing. Sort of like what we saw. And we went back to our diagnostics. We saw a couple of them didn't work, had failed or something, or didn't switch on properly. And we're like, okay, we've got to do this again. All right, so we rebuilt the probe head, and we went to do this again. It happened again. But we're watching the diagnostic, everything worked, and we're watching it. And what we saw just blew us away. All the background gas disappeared. We still had a plasma, so the helium was still going there. We still had the plasma, but all the background gas, what we call the recycling gas, disappeared. Now, if you look at the theories, they say when that happens, your plasma performance, the temperature, should go up. And so when we went back to look at the temperatures, sure enough, our temperatures skyrocketed. And that was why we were melting this stuff. Normally, in our high recycling plasma, no problem, the temperatures only got to about 700-800 degrees Celsius. Yeah, our thermocouples, everything was failing because we're going beyond their limit, which is 1500 kelvins, and well, if you melt molybdenum, that means you got to at least 2800 degrees, and if you're probably welding it to tungsten, you're probably pushing over 3,500 degrees. So, that's those are sort of indicators of just how hot this thing got. But it was amazing. And that one shot, the amount of information we got and what it told us, how lithium was interacting with the plasma, how the plasma was then reacting to that, which was then reacting back to the surface, really told us and pushed us a lot. So from there, we really went and had fun. We probably ran this another 20 times, every single time, same effect. So this was not a one-off fluke. This was a true pumping of the helium. And this is the thing. We were pumping helium. It's an inert gas, something that everyone struggles to pump. And we were doing it no problem. And so this is when I talked about the flexibility. We were going down one path, and we've gone, well, hold on, no, there's a whole other new thing we've got to do here, right? Because this potentially is even more important than what we were looking at before. And this is, we might have a way to solve the helium problem for fusion. And so that's been a big focus of what we're doing. And in that, you also need to understand how does it perform when you have hydrogen in there. So we're sort of building up all this knowledge of not just helium, but hydrogen, mixtures of hydrogen and helium. You know, we're going to be doing that next year. We're going to be starting that. Because you need to know whether all this works together or does it work one off. And with that, you know, we had these results. We then went to Magnum PSI, which is a linear machine in the Netherlands. And Tom Morgan, the great guy, always willing to help out. We were like, hey, can we try something on Magnum? Because they're like the only other machine that runs liquid metals and lithium. And so can we do a lithium test in helium? But all we want to do, we don't care about we just want to see, does the background disappear, right? And sure enough, we saw exactly the same effect. We then convinced East in China to run some helium experiments for us. We saw the same thing. So it's a real effect that is not dependent on the geometry of your machine. The question is then, why? Right? And that's still sort of an ongoing thing that we're trying to figure out, but we think we have a good idea on what's happening there, because lithium is very reactive, but helium is not. So, you know, how does that work? And that's all got to do with your lithium ions that you ionize, and they follow the magnetic field lines, or they co-deposit, and basically will, like a blanket, just start covering the helium and trapping it and not letting it out. And until you give it some energy outside of, you know, to release it. And so it was those results, and then with stuff that Professor Ruzik did back in, and his team, Martin Nieto and all those guys in 2005, where they actually showed that liquid lithium, flowing lithium, could transport helium. They find helium ions into the lithium and transport it into another separate chamber. They were like, okay, we have a way to get the ions in a reactor, and we know that it will get transported. If we can build a flowing diverter, we've probably got a way to get the helium out. So, and I should say also, so to prove sort of our thoughts on this co-deposition, the way that the lithium suppresses the helium, when we were doing this a few years ago, I was like, told my student Andrew, I was like, let's try it in argon. If this is really what this is, this should work on argon. Sure enough, it worked on argon. So yeah, it's and the materials side, the physics, probably don't need to get into it for this, but it's fascinating why it happens and how it happens, because it's I think it happens not intuitively, or what people don't realise. There's a lot about lithium people don't understand about that atom and the way it behaves. So yeah, so that's sort of the the exciting thing, and we're now currently we're designing a full lithium loop for HIDRA. So we'll have one of these hopefully in a year and a half or so operating.
Very exciting.
Yeah, in my opinion, what you discovered, I think it's really important, and I found that really impressive. And about that, like the fusion in a global scale is in development, and it's really fast. It's growing rapidly. And in your opinion, what is the state, if I can say, of the fusion development worldwide, and what is your opinion about certain big machines like HIDRA or some machines like that.
So, ITER, let's start with ITER. ITER's been around for as long as I've been in the game, right? It was the first ideas of ITER came, well, I think 1988 or something, or 1990 was when the first sort of conceptual designs came out for it. In many ways, ITER it's a 1990s machine. But that's the beauty about this. There's a lot of technology, things have updated, right? But the basic concepts, date back to the 50s and 60s, the way these things operate. The way a tokamak operates has not really changed fundamentally, or a stellarator. Despite all the delays, despite everything with ITER, ITER is still going to be one of the, or if not the most important experiment we're going to have. Because despite all these companies, a lot of these companies, they're all talking about, oh yeah, we want to do a Q equals 1 or Q equals 2 machine. Which is like, okay, that's great. But ultimately, if you want a power plant, you need to be operating at about a Q equals 20 or more, right? Let's say Q equals 20, around that. Or Q, depends who you talk to, it's 15 to 20 or so, around that. The jump from a Q equals 1 or 2 machine to Q equals 20, that's an order of magnitude jump, right? ITER is being designed to come in at Q equals 10, right from the get-go. So that jump from 10 to 15 or 10 to 20, it's only now a factor of 2, not an order of magnitude jump, right? So your design process, to go from here to here is going to be, I wouldn't say much easier, but it's a smaller technological jump, I feel, than going from a Q of 1 or even less than 1 to have to go straight to 20 to make it economically viable. And that's only for, I should say, really for a toroidal system. Right, lasers, if you go IFE, they need to push to a Q of 100 or 200, right? Because lasers are just making a laser so inefficient, right? So by the time that light, what people don't talk about with the NIF results, which are fantastic. I think they're now at Q equals 4. I think they're the most recent, right? But no one, right, that's a Q scientific. That's just, okay, the laser energy. How much energy was expended to get that 2 megajoules of energy? A few hundred megajoules from the wall, kind of thing, or more, right? Right. So to get to a just to a break even from a commercial standpoint, they need to get to a Q of 100 or 200, and then they need to go another order or a couple, 10 or 20 beyond that. So I think it's a much bigger technological jump there. Not to say it can't be done. I hope they can do it, but something like ITER is going to be really, really important from that point of view. All these private fusion companies, again, if they can get the funding, they can get the backing, they can do things much more nimbly. Maybe they might beat ITER to the punch, right? I don't know, but we'll see that the first true, toroidal, Q greater than 1 machine, it's either probably going to be tokamak energy or Commonwealth fusion, I would say. They're I would say the 2 most advanced, companies right now, I mean, talking about energy, has machines. They've built machines, and one of them most recently got the 100 million degree ion temperatures, which are required for only 100 milliseconds or something, but that's a big stepping stone, right? So, you know, they all have, they have their roadmaps, their plans, where they want to get to. So we'll see. It's exciting. Like when I started out in the game, was there even the private fusion? Maybe Tri-Alpha TAE had just formed. 2000, around there, 99, 2000, maybe they just formed. And now we're talking about 54 companies. Right? It's pretty amazing, you know. Over $10 billion of investment, you know, maybe more even now. Don't know what the latest numbers are, but, you know, I think it's awesome. You know, you know, someone out there, you know, is going to have the design that will work. You know, and I'm all for all these other, you know, crazy people say, oh, you know, it's a crazy design. Yeah, but you never know. You don't know until you try it, right? That's why we do what we do. You know, that's half the fun. So I've got a crazy idea. Let's give it a go. You know, so yeah, I think it's exciting. I think it's, and look, at some point, some of these companies are going to fail. I mean, that's just normal how all this goes. I mean, in the tech industry, companies come and go on that. But, you know, that's just the way it is. But you then, you know, just have, you work with the next people.
Very exciting.
Yeah.
So, you know, building off that, like, you know, many years in the future, what role do you see as like fusion having like in our energy landscape?
Yeah.
Like, you know, I know some people say maybe it'll power a city, maybe it'll be like everywhere. You know, where do you see it, and how long?
Yeah.
You know, do you think?
So fusion. Okay, so climate change to one side. Okay. The most important thing that we need right now is energy security. Why? If you look at the United Nations Human Development Index, right? It's this curve that goes, so it has this kind of asymptotic, you know, sort of curve to it. And you basically, it's on a scale from 0 to 1. 1 being you have the perfect society, right? On the x-axis is the amount of energy per person per kilowatt hour that's expended. All the countries, you know, the first world countries, the developed countries, the United States, Australia, Europe, they're all over here on the asymptote, somewhere between 0.9 and 1. Right? They have the good life. They have access to everything, food, water, and everything. They all have access to energy, lots of energy. Right? I think the US is something like 12,000 kilowatt hours per person per year that we have access to. If you look at the developing countries like China and India, they're further down around 0.6 or 0.7. They're doing everything they possibly can to get all their people up over here on the curve. That's what they're doing. You know, China and India, if you go and have a look at what they're doing in terms of their energy, they're building everything. Yes, they're still building coal. They're building, you know, gas plants, but they're building solar, wind, nuclear. They're putting a lot into fusion development. They just need energy. That's all they need. That's all they care about with this. They want to get their people over here, right? So that with the sort of coupled also with now we've got the rise in AI and all that, means that we need to find new sources. Not new sources, but we need to find sources of extra energy. The low-hanging fruit, the short to medium-term solution is fission, not fusion. Even if, let's say, in 5 years' time, we get a fusion reactor that goes Q equals 2, it's maybe going to take another 5 or 10 years till we get a Q equals 20. We're not going to just all of a sudden overnight go and replace all 30,000 power plants with fusion plants, right? It's going to take at least 100 years till fusion even gets to something like 10 or 20% of the energy market, the way fission is, right? Fusion is a well-known technology. We know how to do it. We know it works. We know it's safe. We can start deploying that quickly. So the short to medium is fission, plus other renewables in the right places. So I think I've always said, the energy market is horses for courses, right? You're not going to out in the outback of Australia in the desert. You're not going to go and stick a nuclear power plant to power a little town of 30 people. No, you can have a solar plant there, right? So you put things that make sense. You put them where they make sense. So a fusion power plant, it's going to be no different to any other fission or coal power plant in terms of the amount of energy output. It's just a different way of producing that energy. Everyone sort of thinks it's this amazing, you build one reactor and it's going to power the whole country. No, it's a regular power plant, right? Still, if you build it for a gigawatt, it's going to put out a gigawatt of power. If you build it for 100 megawatt, it's just going to put out 100 megawatt of power. So it's just a different way of producing that electricity. So eventually, but the game with fusion is that we potentially have unlimited fuel resources in the deuterium. I remember, I've done this calculation a couple times. I think it's something like 10 billion years worth of deuterium on Earth. Right? It's basically the age of the universe, before you'd run out of deuterium. And it sort of gets renewed a little bit through cosmic rays and that over time anyway, so, and you can probably make it in. Tritium's that's our big problem, but if you can breed it, make it your own, then you've sort of solved that issue as well. But yeah, it's that's, I think, the timeline with fusion, and can it eventually be the thing that replaces everything? I mean, maybe. Do you want it to? I don't know. It's like, right now, I mean, it's not like coal is everything, or all the different power sources have their own chunk of the energy market. I think fusion will be the same. How big it will be, I don't know. Market forces will determine that, I would say. But you look at countries in the US, it's what, 20% of the US electricity. You go to France, I think it's what, 85% or something around there, right? It will just comes down to what the market in that country sort of determines should be. Yeah.
Really.
So it's probably why ITER's in France, because they have this nuclear. They have the mindset, they have the facilities and how to deal with all that. So it sort of made sense to put ITER in France just from the nuclear standpoint, because they have all that expertise. Yeah.
Very, very cool. Okay, so to even, that's a ways away, right? But to even get to that point, what are the current biggest challenges that fusion is facing right now?
Yep.
And how are we combating those? What experience are we?
So I mentioned the helium problem. So that's one. People will debate if it's the most important or not, but it's a major issue. So we can certainly, I've talked about how we can deal with that. But the other one is just the materials. So right now, the there's a thing called the diverter, which is basically the exhaust system. You know, you have your donut shape along the bottom or on the top. You know, you have these kind of areas where we can channel the plasma. So when the plasma comes out through the magnetic fields, we can then channel it along the magnetic fields into the diverter. The plasma has to hit the surface there, right? That's a given. The heat fluxes, that are on that surface can be astronomical. So to give you an idea, the heat landing on the surface of the Earth from the sun is about 1,000 watts per meter. If you burn wood or something, it's anywhere between 10 to 100 kilowatts per square meter. If you have a rocket nozzle, right, the perpendicular, so the stuff coming out, but the stuff that hits on the side, you want it to be no more than 1 or 2 megawatts per square meter, because otherwise you'll start melting it. That's when a lot of the failures happen, something happens and you get a high heat flux that melts it. Or the stuff coming out is way more. Tungsten, which is what we have now, can only handle 10 megawatts per square meter before it will fail, before it will melt. A welding arc is about 40 megawatts per square meter. The surface of the sun is 60 megawatts per square meter. The parallel heat flux from a rocket nozzle, like from a SpaceX or something, is about 100 megawatts per square meter. The heat flux from a fusion reactor, let's say if we have an instability, a transient, that will hit your diverter, can be anywhere from 100 to over 1 gigawatt per square meter. We have nothing that will survive that. Everything will melt in milliseconds when you have those kinds of heat fluxes. So, materials. If we can't find the material or a way to mitigate that heat, or find operating scenarios where we don't have those high heat fluxes, then everything we're doing is going to mean nothing if we can't actually, if when we switch on the machine, we just melt a hole through it. Pointless, right? So the materials is, I think, the most important thing. You know, quite often, you know, you see all these things, you know, with the plasma physics and that, which is important. I mean, you need the confinement of that, but all that means nothing if you can't actually have a machine that can hold it, you know. And you know, Mother Nature has told us how to build a fusion reactor, right? We have one that you know is with us all the time, right? The sun, and one of the things that you know I try to get to when I talk about this, you know, to students and that, is I always pose a question: why does the sun work? It's not how. We know how it works. Okay, we know gravity. You have the weight of all the mass. At the center, you get the pressures, you get the temperatures, you get fusion, you get the heat diffusion and heats and keeps everything hot, right? But why does it stay hot, the sun? And this is the why. Why does it stay hot? Why isn't it cooling down? And again, like I said, Mother Nature, the universe has shown us why. If you have a look at the surface of the sun, it's very dynamic. You get the solar flares and all those instabilities. They inject material out into space, right? Where does it go? Where does the material go?
I don't know. Anywhere? Here even?
Yeah,
Here.
it keeps going out. It doesn't come back in, right? The problem with the fusion with our reactors is when our materials go out, they hit the surface, they cool down to the temperature of the surface. Even if you're running at 1,000 degrees, 1,000 degrees compared to 100 million degrees, which is what we have inside the reactors, is cold. So you've got cold gas, neutral gas, which isn't affected by the magnetic field, comes back and interacts with the plasma. that plasma now has to expend energy to try and reheat and reionize that gas, right? And in doing so, as long as you've got cold gas coming in, you're going to keep losing the energy, right? And so you're always fighting a losing battle. So we struggle because we have a wall. The sun exists. Why does the sun exist? Because it has no wall. Right? The universe tells us, get rid of your wall, you can have a fusion reactor. So how do you get rid of the wall, but still have a wall in a fusion reactor? And that's where lithium, using the lithium. Lithium will absorb all the stuff that comes out of the plasma. You can take it, absorb it, it can deal with a lot of the heat, we think. It doesn't allow that cold gas to come back. And so all of a sudden, this is what happened in hydro, what we saw with helium. It stopped the cold gas coming in, so the energy from the plasma was not getting lost. It stayed in the plasma. Therefore, if you're not losing the energy, you put in more and more energy into your plasma, the temperature has to go up, and that's what we see. Yeah.
Very cool.
Yeah.
Yeah. Mother Nature always beats us to the punch, right? In fission with Oklo, Mother Nature, 4 billion years ago, built the first fission reactor, right? Ran the first reactor, and it took us 4 billion years later to figure out how to do it ourselves, right? So it's always Mother Nature.
Yeah.
Always look to Mother Nature.
Really helpful,
Yeah.
I think we can say.
Absolutely. So, as we're coming to close here, we're talking a little bit off camera, a little bit of about sports and stuff.
Oh yeah.
So we wanted to ask you finally, like, what are your hobbies? What do you do outside of school, outside of teaching, outside of research? We know you're a big Illini football fan.
I am. Yeah, I am.
So
I love sport. I grew up with sport. From Australia. I think if there's a country that loves sport as much, if not more than the US, it's Australia. I mean, it's ingrained in us from day one. Whether it's one of the football codes, rugby league, rugby union, Aussie rules, soccer or cricket or tennis or swimming, surfing. We all love it. Race car driving. I mean, race car driving is huge in Australia as well. We all love it. Everyone's an expert, an armchair expert on every sport kind of thing. So coming here, the whole culture around college football, I love the whole community we love it. Tailgating was the thing that really got me. Well, what you guys have a party in the parking lot for 6 hours before a game? Yeah, I'm into that. Yes, I agree on this. And I will quite happily not just participate, I will organise and run these things. So as I don't know if you've been to any of my tailgates, but I will get there at 5 a.m. and I will, even for a 6 p.m. game, I'll be there at 5 a.m. and go all day, and we have a lot of fun. With music, TV, we grill. On the big games where it's just something special, we do like fish fries or I've been on tailgates where we've got lobsters flown in from Maine and stuff. So that's always been fun. Outside of these days, hobbies. My children are my hobby. It's really now it's just their lives. They're doing swim and piano and basketball and it's just now seeing them develop. That's sort of a great love of mine. Just seeing them becoming the personalities, the way they're developing, the people that they're starting to become. My son's really getting a bit of that scientific and engineering brain. My daughter, I think I'm starting to see those kinds of inklings, but she's very artistic. She's got very much of an artistic. And I think she's going to be the athlete. That girl she can jump and she's contort her body and so I think I'm going to get her into gymnastics or something I think she's going to be the athlete. But I grew up. I played tennis really competitively, ultimate frisbee competitively, played rugby league competitively, these days age and injuries have sort of caught up with me, so I don't do it as much. But these days it's more just I like to go for a bike ride or go for a walk somewhere, or just just going out playing catch with my son. He's got a good arm on him. He's got a good spiral. When he throws a football, so who knows? Maybe he might be football. He's baseball. I really got into baseball. I love baseball as well. Baseball, football, college basketball. My wife's a big college basketball person, so I've got into having a good basketball team as well. Helps.
What baseball team do you support?
Cubs.
I'm a White Sox fan
myself. I've been to the stadium. I'm going to always call it Comiskey as well, even though it's not really the new stadium. It's not Comiskey, the old Comiskeyville, but you've got to call it that. But I've been to a couple games there. I saw the White Sox play the Yankees, and they beat them actually several years ago. So that was fun. But
one day that won't be surprising.
yeah. So it's funny because when I first arrived here, just some of the friends, some of the people I hang out with, they were all Cubs fans. So I was like, Cubs, Bears in the NFL, Bears and Bills. So Bears again because that's what the team when I came here, but I've now taken on the Bills as well because that's. My wife's family's from up around that area, and they're huge Bills fans. And, well, they're having a good run, so it's nice having supporting at least a winning team in that. But yeah, I've enjoyed I enjoyed learning all about football. Some of the players I didn't see what the commentators, but I get the basics of the rules at least. So I follow that. So, but yeah, I mean, I've done a lot in sport myself, not just playing, but also administratively for several years. While I was in Germany, I actually ran a consultancy business in rugby league. So rugby league is so most people will probably know about rugby union, 15-man rugby league is 13-man rugby. It dates back to 1895 was when the split happened. I think it's the far superior version of the sport. It's much faster. It has very much the structure of America. A lot of Americans really enjoy it because it has that sort of a similar structure to American football, so you can follow the offensive and defensive lines a lot easier. You have a tackle count, sort of punting and all that happens. But it's a sport that is still growing a lot worldwide, and I spent a lot of time helping countries and clubs around the world develop the sport. I was helped the sport to begin in Poland, so my background is Polish. So I'm actually considered the grandfather of Polish rugby league, and they had a trophy named after me for the national title.
That's
awesome. I played for the Andruczyk Cup.
That's really cool.
Picture somewhere, yeah. It's a big kind of glass, shattered glass kind of cup, kind of like that big. I've been out there to present the trophy to the winners and that as well. So.
That's awesome.
Yeah,
that's very cool.
Yes, I do. Yeah. I've done a lot of interesting stuff. That's for sure. But
yeah, thank you so much.
Thank you very much.
Yeah, thank you for coming and talking to us. I feel like we all learned a lot.
Yeah, it was a really interesting, and we can really see that actually fusion is probably the most developed developed department here, maybe at the university and maybe in the entire world. So yeah, I think we
Well,
learned a lot.
we're certainly up there. I don't know if in our department, it's certainly I think a nice, it's a cornerstone of the department. But certainly, we have a lot of collaborative work with the nuclear professor, because there's. I didn't talk about the neutronics, but I'm not in neutronics, but I mean that's the nuclear guys department, and a lot of them are now interested in the neutronics for fusion, and that is really important. So I do with the plasmas, but fusion has so much that it needs that are not even plasma related. That you need nuclear engineers, mechanical engineers, chemical engineers, civil engineers. We need everyone. Fusion needs everyone to make this happen. It's not just us plasma guys. Everyone is needed.
Collaboration.
Collaboration. Yeah, for sure. But yeah, this was fun.
Thank you.
Thank you very much.
One day we should do a part 2. Maybe.
Yeah. I'm sure there's a lot more we could talk about.
Yeah.
Oh, listen, you know me. I could go all day. I could go all day. So, but this was a lot of fun. I enjoyed this. Yeah,
Thank you very
this was
much.
great.
Yeah, well, thank you so much for coming and talking to us.
Yeah.
And thank you for telling everybody about your story, your takes on fusion, a lot of the science and everything. It's been a really good time.
Thank you.
Great. Awesome.
Well, thank you very much.
Thank
Yeah.
you.